And now in this lecture we find out the radius of the small circle. In the drawing we have a quarter circle, AOB is a quarter circle. You know that the radius of this quarter circle OB equals to 16 units in its length. Inside this quarter circle we have this semicircle, this is a semicircle, and we also have this small circle. And our mission is to find out the radius of this small circle, or the value of r, that is the radius of this small circle. Okay, so we know that the radius of this quarter circle equals to 16 units in its length, so AO equals to 16, because it is the radius of the quarter circle, of course. It equals to 16 units in its length. We define the center of this semicircle, this point, as point P. We define the center of this small circle, this point, as point Q. The radius of the quarter circle AO is 16, but AO, side AO is also the diameter of this semicircle. So know that the diameter of this semicircle is 16, and therefore the radius must be equal to half of it. That is to say, the radius AP of this semicircle equals to 8 units in its length, and the radius PO also equals to 8 units in its length. So PO also equals to 8 units in its length. This is the radius of the semicircle. Because of the fact that AOB is a quarter circle, angle AOB must be equal to 90 degrees in its size. This is angle AOB, that is equal to 90 degrees in its size, because AOB is a quarter circle. We define the point of tendency of tangent OB with this small circle, this point as point M. Here we can implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing you have a circle and we have tangent AB. This is tangent AB. This is tangent AB. That is tangent to this circle at this point, point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM of this circle that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size. We can actually implement rule 1 in our drawing. We have tangent OB, and we have the radius QM is drawn to point M, that is the point of tendency of tangent AOB. We have the radius QM that is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we'll do a construction. That is to say, from point Q, that is the center of this small circle, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we can get quadrilateral edge OMQ. Inside this quadrilateral edge OMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HQMO we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a right angle, if not a square. So we relate to this quadrilateral HQMO as a right angle because it has 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So a right angle HQMO, side QM must be equal to the opposite side HO. But QM is R, therefore HO must be also equal to R. What is the length of this small line segment PH? From the drawing, it is very easy to see that PH equals to PO minus HO. Again, PH equals to PO minus HO. So write it down. PH equals to PO minus HO. So PH equals to PO. PO is 8. It is the radius of the semicircle that is equals to 8 units in its length. Minus HO. HO is R. Just write down for that HO equals to R. So in total, PH equals to 8 minus R. PH equals to 8 minus R. So I'll write it down here. That PH equals to 8 minus R units in its length. Here, this small circle touches the semicircle at this point. This is their touching point, so we define their touching point as point S. So here we can implement rule 10. Actually, the small circle have an external notch with this semicircle. Actually, they are touching each other externally, it's point S. For that reason, you can implement here rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the side line, here we can see that this small circle touches this big circle at this point, point P, so they touch each other externally at point P. And therefore, according to this rule 10, the straight line that connects their centers together, the center of this small circle is here at point M. The center of this big circle is here at point O. And the straight line that connects their centers together is OMO. The straight line is MO. According to this rule 10, the straight line MO must pass for point P, that is their touching point. Or MPO is one straight line. Again, MPO, according to rule 10, this rule 10 is one straight line. We can implement rule 10 in our drawing. Why? Because in our drawing, this small circle touches this semicircle at point S. So they have an external notch between them at point S. The center of this small circle is here at point Q. The center of this semicircle is here at point P. And the straight line that connects their centers together is of course PQ. And according to rule 10, the straight line PQ must pass through point S, that is their touching point, or PSQ is one straight line. Again, PSQ is one straight line according to rule 10. Okay, so we conduct with PSQ by straight line. Okay, you can see here that the straight line that connects their centers together, that is to say, the straight line PQ passes from point S, that is their touching point. But, or PSQ is also a line, or therefore PQ is also a straight line, of course. But what is the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and that's at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units in its length, according to what we have already found out. So PS equals to 8. And what is the definition of this line segment? Line segment SQ. Line segment SQ starts from point Q, that is the center of the small circle, and ends at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R. Therefore, in total, the length of line segment PQ is 8 plus R. Again, the length of line segment PQ is 8 plus R. So I write it down. PQ equals to 8 plus R. And it is, of course, a straight line. Okay? PQ is a straight line, and the length of this straight line PQ is equals to 8 plus R. In the next step, I will copy the right green triangle PHQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the hypotenuse PQ equals to 8 plus R. And we already found out that PH equals to 8 minus R. HQ is the missing side. Here by PT is a relation from Pythagoras theorem. This is right triangle PHQ with the going from the original drawing. According to the Pythagoras drawing, in this right triangle PHQ, PQ square, that is the square of the hypotenuse, must be equal to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square, plus HQ square. HQ is the missing side, so we leave it as it is. So according to equation 1, we found out that 8 plus R square equals to 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation, equation 1, And we get here that 8 plus r square, 8 plus r square equals to 8 squared, that is 64, plus r square, plus 2 times 8, that is 16, times r. So it is plus 16r. And the other side of equation 1, we have 8 minus r square. 8 minus r square equals to 8 squared, that is 64, plus r square, minus 2 times 8 is minus 16, times r. That is minus 16r, plus hq squared. So here we have 64 on both sides of this equation, equation 1, so 64 will get cancelled. And we have r square on both sides of this equation, equation 1, so r square also will get cancelled. So what is left from equation 1 after we cancelled those two expressions? What is left is definitely in this side of equation 1 we left only with 16r. In the other side of equation 1 we left with minus 16r plus hq squared. So actually according to equation 1 we actually found out that 16r equals to minus 16r plus hq squared. Here we get 16r to this equation, equation 1. Finally we get that according to this equation, equation 1, 16r plus 16r is 32r. So 32r equals to hq squared. Here we substitute 32 by 16 times 2, 2 times 16. So according to equation 1, 16 times 2 times r equals to hq squared. So here we take a root out of this equation, equation 1, and we get that according to this equation, equation 1, hq equals to the square root of 16 times 2r. The square root of 16 is 4. So inside the root we left only with 2r. So actually found out in conclusion that hq equals to 4 times square root of 2r. Actually this side hq equals to 4 times square root of 2r. But we have already found out that this quadrilateral HQMO is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side OM. But HQ is 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2r. From the moment it is very easy to see that this small circle touches the big quarter circle here at this point, this is their touching point. We define their touching point as point T. Actually, we can say that in the drawing we have an internal notch between the small circle and the big quarter circle. That is to say, they are touching each other internally at point T. And for that reason, we can implement here rule 10. Whenever you have an internal notch between two circles, or semicircle and circle, you can definitely implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, here we have this small circle touches the big circle internally at point P. That is to say, they have an internal notch between them at point P. And according to this rule 9, we know that the center of the big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM, of course. And according to this rule 9, the straight line OM must pass through the attaching point, that is point P. Or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Why? Because in our drawing we have the small circle touches the big quarter circle internally at point T. the center of the big quarter circle is here at point O. The center of this small circle is here at point Q. And the third line that connects the centers together is the third line OK, OQ, the third line OQ. And the third line OQ, according to rule 9, must pass through the attaching point, that is to say from point T. Or OQT is one side line. According to rule 9, OQT is one side line. So we connect point O and Q together. So the third line OQ that connects the center of this small circle in the center of this quarter circle passes through point T, that is the attaching point. Or OQT is one side line. If OQT is one side line, OT is also a side line. Okay, OT is a side line. But what is the definition of the side line OT? The side line OT starts from point O, that is the center of the quarter circle, and ends at point T, that is a point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle, that is equal to 16 units according to what is given as the question. So I write it down. OT equals to 16 units in its length. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and then at point T, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. What is the length of line segment OQ? From it is very easy to see that OQ equals to OT minus TQ. Again, OT minus TQ equals to OQ. So I write it down. OQ equals to OT minus QT. So OQ equals to OT. OT is 16 minus QT. QT is R. So in total, OQ equals to 16 minus R. So I write it down here. OQ equals to 16 minus R. In the next step, I'll copy the right blue triangle OQM in a new page, and we will implement the Pythagoras theorem on this right blue triangle OQM. Side QM equals to R, it is the radius of the small circle. Just right now found out that the hypotenuse OQ of the blue triangle OQM equals to 16 minus R. And we already found out that side OM of the blue triangle equals to 4 times square root of 2R. Here by PT is the operation for Pythagoras theorem. So actually, this is the right triangle OQM that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OQM, OQ square equals to QM square plus OM square. The hypotenuse OQ is 16 minus R, therefore OQ square is 16 minus R square, and it is equals to QM square. QM is R, therefore QM square is R square plus OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square. So according to equation 2, we shall find out that 16 minus R square equals to R square plus 4 times square root of 2R square. Here we'll open the brackets on both sides of this equation, equation 2, and get that according to this equation, equation 2, 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is minus 42 times R. And it is equals to the other side of this equation 2, we have R square plus 4 times square root of 2R square equals to 4 squared, that is 16, plus square root of 2R square. The power cancels the root and we're left only with 2R. So in total the value of this expression equals to 16 times 2R. So according to equation 2, we can find out that 256 plus R square minus 32R equals to R square plus 16 times 2R is 32R. Here we have R square on both sides of this equation, equation 2, so R square will get cancelled. After we cancelled R square, in this side of this equation 2, we left only with 256 plus 32R. In the other side of the equation 2, we left only with 32R. So here we add 32R to this equation, equation 2, and finally we get that according to this equation, equation 2, 256 equals to 32R plus 32R is 64R. Here we divide this equation, equation 2 by 64, and finally we get that according to this equation, equation 2, R, the radius that we are looking for, of the small circle equals to 256 over 64 is 4. So R equals to 4 units in its length. Repeat again. The answer to the question is that the radius of this small circle R equals to 4 units in its length. So in the next step, I'm summarizing the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have a quarter circle. AOB is a quarter circle. You know that the radius of this quarter circle equals to 16 units in length because OB equals to 16. Therefore, the radius AO is also 16. The radius of the quarter circle. Inside this quarter circle, we have this semicircle, and also we have this small circle. The small circle touches this semicircle at this point. This is the touching point. Okay, repeat again. Our mission is to find out the radius of this small circle. Repeat again. The radius of the quarter circle is 16. Therefore, AO equals to 16, and OB is also the radius of this quarter circle that equals to 16 units in its length. Because of the fact that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. In addition, we can implement here rule 1 because we have tangent OB is tangent to this circle as point M. Point M is the point of tendency of tangent OB with this small circle. And we have the radius QM that is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay. In the next step, actually, we did a construction. We defined the point, the center of this semicircle, this point is P, the center of this small circle, this point is point Q. And from point, in the next step we did the construction, that is to say from point Q, we do perpendicular on AO. Again, from point Q, we do perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO, this point is point H. By doing this construction, we created the quadrilateral edge O and Q. This is quadrilateral MO, edge O and Q. Inside this quadrilateral edge O and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HOMQ we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we relate to this quadrilateral HOMQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle HOMQ side QM must be equal to the opposite side HO. But QM is R, therefore HO must be also equal to R. HO equals to R. PO equals to H. So what is the length of this small line segment PH? PH equals to PO minus HO. Again, PH equals to PO minus HO. So PH equals to PO, that is 8, minus HO, that is R. So in total, PH equals to 8 minus R. And this small circle touches the semicircle at this point, point S. Point S is their touching point, or their points of tendency. Actually, the small circle has an external notch with this semicircle at point S. Whenever you have an external notch between two circles, you can implement rule 10. Repeat quickly rule 10. According to rule 10, if two circles touch each other externally, here this small circle touches the big circle at point P. That is to say, they are touching each other externally at point P. Then, according to this rule 10, we know that the center of this big circle is at point O. The center of this small circle is at point M. And the straight line that connects their centers together is the straight line MO. The straight line MO, according to this rule 10, must pass from point P, that is the touching point. Okay, or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing, point S is the touching point of this semicircle in this circle. That is to say, there are external notch between them at point S. Therefore, we can implement rule 10. According to rule 10, we know that the center of this small circle is at point Q. The center of this semicircle is at point P. And the straight line that connects the centers together is the straight line PQ. So according to rule 10, the straight line PQ must pass through point S. That is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line, and therefore PQ is also a straight line. What is the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units according to what we already found out. What is the definition of line segment QS? Line segment QS starts from the center of the small circle, that is to say from point Q, and ends at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore QS is the radius of this small circle that is equal to R. So in total PQ equals to 8 plus R. And again PQ equals to 8 plus R. And in the next step, so I copied this green rectangle PHQ in a new page and implemented the Pythagoras theorem on this right green small triangle, green triangle PHQ. This is the green right triangle PHQ that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle PHQ, it means that PQ square equals to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. So according to HQ is the missing side, so we leave it as it is. So according to equation 1, we actually found out that 8 plus R square equals to 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation, equation 1, and found out that according to this equation, equation 1, 8 plus R square equals to 8 plus R square equals to 8 square, that is 64, plus R square, plus 2 times 8, it is 16 times R. So it is plus 16R. On the other side of equation 1, we have 8 minus R square. 8 minus R square equals to 8 square, that is 64, plus R square, minus 2 times 8, that is minus 16 times R. So it is minus 16R plus HQ square. Here we have 64 on both sides of this equation 1. Equation 1, so 64 will get cancelled. And we have only we have also R square on both sides of this equation 1, so R square also will get cancelled. After we cancel those two expressions, in this side of equation 1 we left only with 16R. On the other side of this equation 1 we left with minus 16R plus HQ square. So according to equation 1 we actually found out that 16R equals to minus 16R plus HQ square. Here we added 16R to this equation, equation 1. We found out that according to this equation, equation 1, 16R plus 16R is 32R. So 32R equals to HQ square. We substitute 32 by 16 times 2. So according to equation 1, we found out actually that 16 times 2R equals to HQ square. Here we took a root out of this equation, equation 1. We found out that HQ equals to the square root of 16 times the square root of 2R. The square root of 16 is 4, so inside the root we left only with 2R. So in conclusion, we found out that HQ equals to 4 times square root of 2R. This line segment HQ equals to 4 times square root of 2R. But we already found out that quadrangle HQMO is rectangle. And we know that the opposite sides of the rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side OM. But HQ equals to 4 times square root of 2R. Therefore OM must be also equals to 4 times square root of 2R. Okay. In the next step, I copied this right blue triangle. Actually, before that, we have this quarter circle touches this small circle internally at point T. That is to say, they have an internal match between them at point T. Whenever you have an internal match between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass from their touching points. So in the drawing we have this small circle touches the big semicircle internally at point P, and the center of this big circle is 0.0. The center of this small circle is at point M. And the straight line that connects the centers together is the straight line OM. And according to this rule 9, the straight line OM must pass from point P, that is the touching point. OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. One for our drawing, as I already mentioned before, the quarter circle touch this small circle here at point T, so they have interval between them at point T. Therefore, according to rule 9, we know that the center of this small circle is at point Q. The center of the big quarter circle is at point O, and the center line that connects the centers together is OQ. And according to rule 9, the straight line OQ must pass from point T, that is the touching point. OQT is one straight line. OQT is one straight line. Therefore, OT is a straight line. But what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and then at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle. That is equal to 16 units according to what is given as the question. What is the definition of line 7 QT? Line 7 QT starts from point Q, that is the center of the small circle, and then at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. Okay? And we know that OQT is one straight line. So what is the graph of line 7 QO? For the drawing, it is very easy to see that QO equals to OT minus TQ. Again, OT minus TQ equals to QO. Repeat again, QO equals to OT minus QT. So QO equals to OT, that is 16, minus QT, that is R. So in total, QT equals to 16 minus R. In the next step, I copied this blue right triangle OQM in a new page and implemented the Pythagoras theorem with this blue right triangle OQM. This is the blue right triangle OQM that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. We want to find out that the hypotenuse QO equals to 16 minus R units in itself. QM is the radius of the small circle, the radius that we are looking for in this question, and it is equal to R. And we already found out that OM equals to 4 times square root of 2R. So according to the Pythagoras theorem, in this right triangle OQM, QO square equals to OM square plus MO square. Again, QO square equals to OM square plus, again, QO square equals to QM square plus OM square. So QO is 16 minus R, therefore QO square is 16 minus R square, and it is equals to QM square. QM is R, therefore QM square is R square, plus OM square. OM is 4 times square root of 2R, and therefore OM square is 4 times square root of 2R square. Here we open the brackets on both sides of this equation, equation 2, and I found out that according to this equation, equation 2, 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is minus 32, times R. So it is minus 32R, and it is equals to R square, and 4 times square root of 2 R square equals to 4 squared, that is 16. And here the power cancels the root, and we left only with 2R. So this expression in total equals to 16 times 2R. So according to equation 2, we have found out that 256 plus R square minus 32R equals to R square, and 16 times 2R is 32R. So according to equation 2, we have found out that 256 plus R square minus 32R equals to R square plus 32R. So here we have R square on both sides of this equation, equation 2, so R square will get cancelled. So in this side of equation 2, we left only with 256 plus 32R. In the other side of this equation 2, we left only with 32R. Here we added 32R to this equation equation 2, and finally found out that according to this equation 2, 256 equals to 32 hours plus 32 hours is 64 hours. So according to equation 2, 256 equals to 64 hours. Here we divided this equation 2, by 64, and finally found out that R, the radius that we are looking for, the radius from this small circle equals to 4 units in its length. Repeat again, the radius of this small circle R equals to 4 units in its length. Okay, thank you very much.